Welcome to The Explainer. Today we're doing something a little bit different. We're going to look way beyond the raw code. We're going to slow down, take a breath, and really peer into the majestic, geometric universe of data. You see, we often think of artificial intelligence as just endless layers of math and processing power. But beneath all that computation, there is this profound, hidden architecture. Today, we are going to explore the fundamental geometric law that governs exactly how machines learn to imagine. It's a philosophical question, right? But honestly, a totally necessary one. When a generative AI just pulls a photorealistic world, a stunning portrait, or a flawless paragraph of text out of thin air, where are those creations actually coming from? They don't just materialize from nowhere. They're pulled from a highly specific mathematical space. But what does that space actually look like? To understand the magic and the failures of modern AI, we really have to map this unseen territory. Section 1, the AI geometry paradox. So modern generative models, they make this breathtaking art, mimicking reality with astonishing precision. But then they fundamentally break down in these strange, highly predictable ways. We call this an off-manifold artifact. Picture this. You're looking at a stunning, high-quality AI-generated portrait of a person. Now, zoom in on the hand. Imagine a bright red border around it. Boom. 6 fingers. Maybe the teeth are merged together, or there are these nonsensical text loops. You know exactly what I mean, right? Well, this isn't just a random glitch. It is a profound geometric error. The AI hasn't just drawn a bad hand. It literally stepped completely outside the mathematical boundaries of learned reality. Section 2, the empty universe problem. To figure out how the AI stepped out of bounds, we've got to zoom out from that broken image and look at the environment where these models actually operate, the ambient space. Think about a standard, pretty small image. It might have 65,536 pixels. Well, in machine learning, every single one of those pixels is a dimension. So the ambient space for that image, it's a 65,536 dimensional universe. Try to picture that as a massive, pitch-black warehouse stretching out into infinity. And almost every single possible combination of pixels in this huge warehouse is just pure static, noise, or garbage. The actual meaningful images, human faces, landscapes, dogs, they occupy an infinitesimally tiny sliver of this dark warehouse. And this brings us to a huge turning point in AI history. Back in the 1990s, classical machine learning actually tried to model that entire massive high-dimensional space, and it failed. As images got larger, researchers slammed right into a wall known as the Curse of Dimensionality. The data points in that giant dark warehouse were just infinitely far apart, which caused models to wildly overfit. The big breakthrough of modern deep learning was a massive paradigm shift. We abandoned the impossible task of modeling the entire empty space and instead focused strictly on the tiny, structured surface where the real data actually lives. We shifted our goal to parameterizing what is known as the manifold. The data wasn't filling the space was mostly empty. This realization, it's the absolute cornerstone of everything we're discussing today. Think about a high-resolution image of a human face with 100,000 pixels. The variance in that face isn't driven by 100,000 independent factors. No way. It's driven by maybe 20 facial muscles, the angle of the lighting, and the camera position. The space itself is just mostly empty. Section 3, the crumpled paper analogy. Okay, so the crucial point is figuring out how those 20 underlying factors actually exist inside that 100,000 pixel warehouse. To do that, we use what is basically the gold standard analogy in the field. Imagine a standard, flat piece of printer paper. Intrinsically, it's a 2D object, right? Now crumple that paper up into a tight ball and toss it into a massive empty 3D room. If a little ant is walking on that crumpled paper, it only knows 2 dimensions: forward, backward, left, right. The ant is living completely in the intrinsic 2D space of the manifold. It has absolutely no concept of the 3D room around it. But if you are standing in the room looking at the crumpled ball, you see the 3D ambient space. Real-world data like images or text is exactly that crumpled piece of paper. It is tightly confined to a lower dimensional surface, twisted and folded up inside a massive empty universe. And this brilliantly illustrates exactly why standard measurements totally fail in AI. If you pick 2 dots on that crumpled paper and try to connect them with a straight Euclidean line, your line is going to leave the paper entirely and cut straight through the empty 3D room. If an AI generates an image along that straight line, it produces a blurry, impossible blend of empty space, basically a ghost image.
But if you measure the geodesic distance, meaning you carefully trace a solid path smoothly along the curved surface of the paper itself, you get valid, beautiful transformations, a head turning smoothly, a coherent transition. You literally have to stay on the paper.
Section 4. Proving the latent space. So, if the data is a crumpled piece of paper, how does a neural network actually process that geometry? How does a machine learning model running on a GPU actually see the ant's perspective? Well, we can literally see this physical manifestation in the architecture of a variational autoencoder, or a VAE. Step 1. The model takes in the massive high-dimensional input, that full 65,536 pixel image. Step 2. It forces that data through a tiny bottleneck, collapsing it all down into a small vector we call Z, the latent space. And this isn't just compression. Mathematically, the neural network is finding the true uncrumpled shape of the data. It is literally flattening out the paper. Step 3. The decoder then expands it back out, applying the mathematical folding rules to place it right back into the ambient room. Now that tiny bottleneck, it might only be 50 dimensions. And this number 50 represents the intrinsic dimension of our data. Those are the 50 underlying factors, like the lighting, the object identity, the texture, that actually control the tens of thousands of raw pixels. By forcing the data through this narrow little tube, we mathematically constrain the AI to only care about the flat paper, completely stripping away all the empty space and noise of the darkroom. Section 5. Off-manifold artifacts. All right, now that we've wrapped our heads around the paper in the darkroom, we can finally solve our opening mystery. Let's explain exactly why that generative model gave us a six-fingered hand earlier. It all comes down to this. The AI sampler missed the paper and stepped into the empty void. You see, the generative model, whether it's a GAN or a diffusion model, has to learn the exact boundaries of that crumpled paper. If it hasn't learned that boundary perfectly, well, during the generation process, its latent vector might point just a millimeter off the edge of the true manifold. It reaches out into the empty dark warehouse, and it pulls out impossible physics. In fact, almost every major failure you see in generative AI is a specific geometric failure regarding this manifold. First up, we have off-manifold generation, which we just talked about, missing the paper entirely and generating six-fingered hands. Second, there's manifold collapse. This happens when the AI learns a manifold that is way smaller than reality. Instead of a complex crumpled sheet, it just learns a simple flat square, which means it only ever generates one single type of face, over and over, totally ignoring the diversity of the real world. And third, the interpolation trap. Say the crumpled paper is shaped like a horseshoe, and the AI tries to draw a straight line between the two ends. It steps right off the paper into the void. The result, as it smoothly morphs between two faces, it suddenly passes through this grotesque, zombie-like intermediate state. Section 6. The shape of intelligence. Let's bring this whole philosophical journey back into hard engineering and see how these concepts actually map to the real-world models that are completely transforming our society right now. This is where it gets incredibly exciting, because this math, it governs absolutely everything. VAEs map data to a probability distribution directly on that low-dimensional manifold. GAN generators are explicitly built to parameterize the manifold. They are literally engines for folding paper. Diffusion models like Stable Diffusion do something totally wild. They intentionally push data off the manifold into a structureless cloud of Gaussian noise out in the empty room, and then they train a neural network to act like a magnet, learning the exact vector field that points perfectly back to the crumpled paper. And yeah, even large language models like GPT-4 operate in a discrete vocabulary space. When they generate text, they are carefully walking along a discrete grammatical manifold, token by token, making sure they don't just step off into the ambient space of pure gibberish. So, to summarize our core thesis here, every generative AI system is fundamentally an engine for mapping coordinates on a low-dimensional manifold back into high-dimensional space. That's it. The AI does not wander aimlessly through this massive dark warehouse of infinite possibilities. It doesn't search the darkroom at all. It simply draws coordinates on a flat 2D piece of paper and then applies mathematical folding rules to place it exactly where it belongs in our complex reality. We've seen how machines find the smooth surfaces of human faces, the structure of spoken language, and the laws of photorealism, all hidden away like crumpled paper in the dark. But it leaves us with one final, truly mesmerizing question. If all artificial intelligence is simply discovering the inherent geometry of our data, what other hidden shapes are out there, just waiting to be unfolded in the darkroom?